All right, 150, chapter 23, question 2. Here we have two identical conducting small spheres. They are placed with their centers 0.3 meters apart. Okay, so I'm going to start off by drawing my picture as we go here. I'm going to have two spheres. Their centers are 0.3 meters apart. One is given a charge of 12 nanocoulombs. The other has a charge of negative 18 nanocoulombs. Okay, so let's make this one positive 12 nanocoulombs. And we'll make this one negative 18 nanocoulombs. Multi-part question. Part A says to find the electric force exerted by one sphere onto the other. Okay, so we know force could be magnitude of is K, Q1, Q2 over R squared. Okay. And if we plug in what we know that K, 9 times 10 to the 9th. Our Q's here, we have to put in our Q's, so we'd have 12 times 10 to the negative 9th, because that's nano. So 12 times 10 to the negative 9th is our first charge. Our second charge, Q2, these are absolute values, so you do not include the negative, you just treat it as a positive. So it would be 18 times 10 to the negative 9. That's our K, Q1, Q2. And now as far as the R squared, we're looking at 0.3 squared. Okay. If we do that math out, we should hear that the force should be around 2.16 times 10 to the negative 15 newtons. Now, of course, this is just the magnitude. If we are looking for the direction of that force, we'd have to look at the charges. Right? One's positive, one's negative. These two charges are going to be attractive. Okay, so if you want to add in for the direction, it's towards each other. You can also just put attractive. Okay, that these two will be attracted to each other. So this would be part A. Part B says, what if the spheres are connected by a conducting wire? Okay, so if you took the two spheres and you connected them with a wire, find the electric force each exerts on the other after they have come to an equilibrium. Okay, well this one's highly positive and this one's highly negative. So if you were to connect these two with a wire, they're going to share their charges. Okay, and some of them are going to cancel out. The positives and the negatives will cancel and they'll become neutral. So to find out what the average would be on these two charges, we need to take an average. So we're going to add up all the charges. So we're going to have a positive 12 nanocoulombs plus we have a negative 18 nanocoulombs, and we're going to divide by the total number of charges, which is 2. Okay. If we do that, we'd have 12 plus a negative 18 gives us what? A negative 6. Negative 6 divided by 2 gives us a negative 3. So each sphere will have negative 3 nanocoulombs left on it. Okay, you can decipher that however you wish, that 12 of the charges here will cancel with this one, and they'll be shared by the remaining 6 will get shared. However you want to do the math, however you want to think of it in your head, that's fine. But each sphere now will contain negative 3. They are still separated by the distance 0.3 meters. But now we just have two spheres that are negative 3 nanocoulombs. And we just do it again. We find out what the force is now that these two have come to an equilibrium. So to do that, we need K, Q1, Q2, R squared. If we do this out, we'll have 9 times 10 to the 9th. And now the two charges are the same. So we'd have 3 times 10 to the negative 9th squared, and everything remains over that 0.3. 0.3 gets squared because of the r is squared. And I would just plug into the calculator again to find out what the new force is. And if we look at that force, we get 9 times 10 to the negative 7 newtons. Okay? It's actually quite a bit smaller than the other force. 9 times 10 to the negative 7. And also, the direction has switched. Whereas these were attractive because it was positive and negative. These are both negative, which means it's going to be repulsive. Okay. And that would be your answer here for part B.